Let's go ahead and look at this problem here. We're looking for the center of mass, and we're pretty sure what the answer is in the y direction. Symmetry suggests that I've got just as much mass above the y equals 0 line as below the y equals 0 line. So that center of mass has to lie somewhere along that line. Okay, if I could draw, that would be more in the center. Now, the question becomes, where is it in the x direction? And our gut tells us that it's got to be somewhere to the left of x equals 5 centimeters. But we would find that location by doing a weighted average. If I call this wire 1, and this wire 2, and this wire 3, then the center of mass for wire 1 is going to be right here at x equals 5 centimeters. And I would weight that with how many grams that represented. I then would take wire 2, and its center is right here. Well, in the x direction, that's at x equals 0. And I would have to weight that by the 20 grams. And then I would take wire 3, and its center is going to be right there at x equals 5 centimeters. And I would weight it by the 20 grams. And then I would divide by the weighting factors, 20 grams plus 20 grams plus 20 grams. And that's going to give me 200 grams centimeters over 60 grams, and that's going to be 3.3 centimeters. So the center of mass would be a location at x equals 3.3 centimeters and y equals 0. Okay? Check that your neighbor understands that. I mean, that's for the center of mass. That's an x and a y, but you'd probably get full credit if you found the x. Okay. Question? Okay. We're going to start our discussion with a little demo. I have here a setup where I have two spring scales that read forces in newtons. And I've got hanging from those spring scales a rod that is 1 meter long and has a mass of 1 kilogram. I'm going to hang from the center of the bar a 1 kilogram mass. And I would like you, with your neighbor, to predict what the reading on the two spring scales will be. Pretty easy, isn't it? I mean, I hope everyone can immediately see that it's 10 and 10. Because that rod's not going anywhere. And I got 20 newtons pulling down. The earth's pulling with 10 newtons on the rod. This string is pulling with 10 newtons. And that means that the spring scales have to be pulling up with a total of 20 newtons. I've got 10 newtons there and 10 newtons there. I knew the total force up had to be 20, and I knew it had to be split evenly because it's symmetric. But what if it's not symmetric? What if I move this mass over to the right so that it's 80 centimeters from the end? Now there's a heavy end. Now it's not symmetric. Predict the readings on the scales with your neighbor Nimrod. Okay? And when you get an answer, tell me what that answer is. Okay, have we all voted? Okay. The answer is not A. Now that suggests that most of you got that wrong, okay? That a very few people got it right, regardless of whether it's B, C, D, or E. Okay? So let's talk about this. It's not surprising that we got it wrong. This is really a pretest. Notice, before we go on, that all of these combinations add up to 20. 4 and 16, 20. 5 and 15, 20. 6 and 14, 20. Newton's second law is still valid. I still have to balance all the force down with all the force up. So the total force up still has to be 20 newtons. The problem is, without symmetry, I don't know how to divide up those 20 newtons. And so I need something else. I need an idea that we call torque. Now, let's go on that field trip again to the big field of snow where there's that frictionless pond. We're going to lay that same standard meter stick down, but this time we're going to drive a stake, a pivot, through that, the end of that meter stick. And that's a special pivot that is frictionless, okay? We've polished it and we've greased it so that there's no friction there. Now, if we push on that meter stick with two forces, each force 50 newtons, you know that those two forces are going to cancel in a linear sense. 50 to the right, 50 to the left, that adds up to 0. And yet when we're talking about rotation, you can see that it's not a tie. One of those forces is going to be more effective in causing rotation than the other one. Which one is it? Yeah, the one that's further away from the pivot. Okay, you've all experienced this when you're trying to get a nut off of a bolt and it's rusted on, and so you're pulling with your wrench. So what do? You go and you get a bigger wrench so that you can pull further away from the pivot. And if that doesn't work, you get a pipe to put on the end of that big wrench and you pull, way out here. And if you're like me, you break the bolt right off and have to start over. So the further away from the pivot, the more effective a force is in causing rotation. And yet that's not everything. Because if I were to push here and here, F2 is still applied further from the axis, from the pivot point. And yet, how much torque, how much rotation am I going to get out of F2? None. That's a dumb guy force, okay? If you come to a revolving door, I'm not sure they have those in Montana, but in some places they have those. You come to a revolving door and you push like this, they go and get the authority. And you get to toss with somebody, a very friendly person, okay? Now, what we see here is that the angle at which you apply that force matters. How far you apply it from the pivot matters, and the angle at which you apply it matters. Now, in general, what we have to do is we have to define this vector r, the position vector, that starts at the pivot and goes to where the force is applied. The next thing we have to do is define this angle, and listen carefully to my words. This is the angle between the direction of r and the direction of f. Don't ever say it's the angle between r and f, because that's going to make you want to use this angle here. It's the angle between the direction of r, which is towards the ceiling, and the direction of f. So if r is towards the ceiling and f is that way, it's this angle here. Okay? Now, if we define that angle and that position vector, what we find is that the torque, we use the Greek symbol tau, the torque is equal to the magnitude of the position vector, the magnitude of the force, times the sine of the angle between them. Now that sine is biggest when theta is 90 degrees. And the torque for a given position vector and a position force is biggest when they're 90 degrees to each other. Okay? Now, in practice, in 90% of the homework problems, 90% of the exam problems, what you will have is a case where the force and the position vector are already perpendicular. Okay? If that's the pivot and that's the force, that's the position vector. That's what it usually is. And in those cases, it's just very simple. It's just the force times the distance to the pivot. That's the torque. The force times the distance to the pivot. But they have to be 90 degrees to each other. Now, in this case, that would be 3 meters times 200 newtons, or 600 meter newtons. Now, technically, I could call that 600 Newton meters, but I don't. I never do. I always call it meter newtons, because Newton meter has a different connotation. What's a Newton meter? Newton meter, Newton meter, Newton. Joule. Okay? That's the unit of energy, and this is different than energy. This is a different concept. And so I will always call that a meter Newton. Or in America, what do we call them? Foot pounds. Foot pounds. Instead of meters, we have foot. And instead of newtons, we have pounds. Okay. Now again, I can't say this enough. A torque is a force times the distance to the pivot, but they have to be perpendicular to each other. So what if they're not? Well, we have two options. The first option we call the useful force method. We use in this method all of the position vector, but only the part of the force that is perpendicular to that position vector. We break up that force into two components, one that is perpendicular to this r vector, and one that is parallel to this r vector. Now you can think of these two components as forces that are applied right there. In other words, think of these as two strings, one pulling to the left and one pulling straight up, right there, straight up. If I'm pulling right there, straight up, is that going to cause rotation? No or heck no? Heck no, yeah. So this is not giving me any rotation. This is the only part that's useful for causing rotation. Now if I use a little math, trig, actually geometry, this angle has to be that angle by opposite interior angles. And now I use a little trig. This is my right triangle. So this is the opposite side. And that's going to be the force times the sine of that angle. Now if you look at my definition of torque, there's the force times the sine of that angle. That's the useful part of the force. That's the perpendicular part of the force. So we use all of the distance and only the part of the force that's perpendicular to the distance. Okay? Again, torque is a force times the distance, but they have to be perpendicular to each other. And that force is perpendicular to that distance. Now, there's another method. Oh, Greg, don't give me another method. I don't want two methods. Just give me one method. You're going to find in this week's tutorial that this method makes half of all the problems trivial. And the other half of all the problems really, really hard. So we do need another method. And the other method we call the lever arm method. And in this method, we do exactly the opposite of what we just did. In this case, we're going to use all of the force, but we're only going to use part of this position vector, the part that's perpendicular to that force. Now, to use this method, we extend the force in both directions forever, and we call that the line of action. And we say that this force is acting along the line of action, along that line. And then we find the distance that starts at the pivot and comes in perpendicular to that line of action. Now looky here. That force is perpendicular to that distance, and that's going to give us our torque. Now if we do a little geometry again, this angle here has to be how big compared to theta? Well, it's got to be theta, right? Okay. And that means that this blue line is going to be the hypotenuse. There's my right triangle. It's going to be the hypotenuse r times the sine of the angle because it's the opposite side. Now, if I look at my general definition of torque, F r sine theta, that r sine theta is just the lever arm. So the total force times just the part of the distance that's perpendicular to that force gives me the torque. Now again, half of the problems will be trivial with this approach and very complicated with the other approach. Now, as I told you last day, this week's tutorial has no homework, okay? That means it's all attendance. 15 points if you come, 0 points if you don't. So you should go to that tutorial, okay? Now, torque, to wrap things up here, is what causes angular acceleration. Now, that seems familiar. You remember that a net force causes a linear acceleration. And because this causes that, this has to be in the same direction as that. Well, now what we're saying is that a net torque causes an angular acceleration. Okay? An angular acceleration. Now, the direction, therefore, needs to be in the same direction as alpha. And what we found with our alpha is that sometimes we are having an alpha that's out of the page, and sometimes we're having an alpha that's into the page. And so we're going to need a new right-hand rule. Our first right-hand rule was for omega. I take the fingers of my right hand and I revolve them, I rotate them with the wheel. My thumb is telling me the direction of the omega vector. For torque, I do something very different. I start at the pivot and I reach out to where the force is applied. I reach out to where the force is applied. This is the important step. I turn my wrist so that I can girly wave. There, I said it. Okay. Girly wave in the direction of the force. My thumb is pointing in the direction of the torque. Okay. So you start at the pivot, you just reach out to the force, turn your wrist so you can wave in the direction of the force. Your thumb is pointing in the direction of the torque. Now, if that force were acting always at that angle relative to this vector, this thing would start spinning. It would start spinning counterclockwise. What direction would the omega point? Out of the board. Okay? And if it's spinning up from rest, it's speeding up. So what direction would the alpha point if the omega's out and it's speeding up? Out. Okay? And sure enough, this torque is out. It's causing the alpha. It's causing the alpha. Now, let's remember this, I told you we would understand this precession here. You remember the omega vector is the red vector. It always stays the same length, never gets longer or shorter, but it is changing direction. And so that means we have an alpha. And that alpha has to be perpendicular to the omega. Now I want you to take a picture of this system right now. You didn't. Come on, people, work with me. Take a picture of it right now. People, I'm talking to you. Take a picture of it right now. I'll do it. Okay? I'll just freeze time. There, I took the picture. I took the picture right when I was holding this and the alpha vector was moving away from me. Good enough? Everyone got the picture? Okay. Let's see what's causing that alpha. Okay, again, the alpha has to be perpendicular to the omega. So, if the net torque is causing the alpha, and the alpha at this moment we took the picture is pointing away from you, what direction is the net torque? Away from you. Let's show that. Now, here's something new. When we were worried about linear motion, we did not care where the forces were applied. We drew a free body diagram by making any object, no matter how complicated it was, a dot. Because all we cared about was how much force we had to the right, how much force we had to the left, how much force we had up or down. We didn't care where those forces were applied. And that dot represented the center of mass of the object. But when we deal with torque, we very much care about where the forces are applied. So we draw what's called an extended free body diagram. And we draw the object as it appears. And we put on that object the forces where they are applied. Now, in this case, our omega vector is the red arrow pointing towards the open door. The blue vector is the alpha vector pointing away from you. Oops, it's sagging. Okay. Now, if I look at the forces, I have the tension in the rope, and I have the weight force. Now, I applied the weight force here at the center of gravity. And remember, as long as we're close to the surface of the Earth, the center of gravity is the same place as the center of mass. Now, because this wheel is weighted down with lead, all the mass is pretty much here. It's not to the left of there or to the right of there, it's pretty much here. And so I can draw that weight vector as acting right here at the center of the wheel. Now, in order to look for torque, I always have to look for torque about some pivot point. In this case, as I was holding this, it was precessing, it was rotating about this point right here where the rope attaches to the bar. And so that's going to be my pivot right there. Now, let's take these forces one at a time. And we need to talk about what torque do I get from this force. Is it out of the page, into the page, or zero? That one right there. Why is it zero? Oh, not zero? Look at the lever arm. If I extend the line of action goes right through the pivot. There is no lever arm. This is like going up to a door and trying to open it by pushing at the hinge. That doesn't cause rotation. Not about that point. So let's look at so that gives me zero torque. Let's look at the torque due to this weight. I started the pivot. I reach out to the force. I turn my wrist so that I can wave in the direction of the force. My thumb is in the direction of the torque. Now, if I take a zero torque and I add it to a torque into the page, I get a net or total torque into the page, which is causing that alpha. Okay? Check that your neighbor's on the bus. Okay. Do any of you drive a Harley? Come on, you can share it. Okay. No Harley driver. Does anyone know how you turn left on a Harley? You're holding the handlebars and you want to turn left. You just yank the handles, just lean. None of you have done that with a Harley? Okay, it turns out that if you're on a heavy Harley and you want to turn left, you push forward on the left handlebar. That seems wrong. That seems like something your parents wouldn't want you to do. But that's going to actually lay the bike over and make you go to the left. Now, if I think of the front wheel on that Harley, oh man, I'm getting old and fat. Okay. As the wheel is turning, your omega for that wheel is pointing in the direction of the red arrow. Now, if I want to lean this bike over, I want that red arrow to just go down to the ground. Okay? And that's going to happen if I have an alpha in the direction of that blue arrow, down. Now, think about the torque when I push on the left handlebar. Okay, I'm pivoting the bike about that place where the bottom of the wheel touches the pavement, the contact point. So I reach up from that point with my right hand. I wave in the direction of the force that I put on that left handlebar. And where's my thumb pointing? Down towards the ground. And that torque is going to cause my alpha to go down towards the ground, and I will go around the corner. Help, help, I'm stuck. Okay, he made it. Okay. Question about riding a Harley. Another 50 pounds and I can ride a Harley. Got to be a certain weight. Okay. Now, turns out that if a net torque causes an angular acceleration, if I have a zero net torque, that should cause a zero angular acceleration, by which I mean a constant omega. Now, that could either be something that's stopped or something that's rotating at a constant rate, the same omega all the time. And we also find that if we double the torque, we double the alpha. Now on Wednesday we're going to find out what the constant of proportionality is, but for now this is just an observation. Now, in order to solve problems using torque, we need to go back and understand what Friday's lecture was all about. I'm sorry, forgot this was in here. On Friday we decided that the center of mass would seek a point directly below the support. And at that point, it would be happy. Now, if we think of this in terms of torque, if we draw a line of action away from this force, it's going to go right through that pivot point. That means my lever arm is going to be 0. That means the torque is going to be 0. And it's just going to stay right there. If, on the other hand, I slide this over to the right, now the weight force is acting right here, and if I extend that into a line of action, I get a lever arm that's non-zero. That's going to give me a torque that's going to cause rotation back to that place of stability where the lever arm goes to 0. Now, instead of using the lever arm method, I could take the useful force method. If I take all of the position vector and just the part of this weight vector that's perpendicular to the distance vector, I would also have a torque. And that torque would cause it to rotate back to the position directly below the support. Now, here's where we practice so that we can solve problems. Suppose I have a rod that is very strong, but very light. It's made of graphite epoxy. We can neglect the mass of it. And we have it pivoted with a pivot that has no friction. Now, if I were to hang a 200 Newton weight at the end of this, you know what's going to happen. It's just going to fall right down to the ground. It's going to rotate clockwise and hit the ground. Now, if I don't want it to rotate, I'm going to have to pull on it with a force that's equal to 200 newtons. If I put the scale there. But if instead I put the scale there, halfway down the rod, how hard am I going to have to pull with that spring scale to keep it from rotating? Yeah, the answer is 400. But why? But why? Let me explain that. In linear motion, if you've got some object that's not accelerating, it's just sitting there, and if I told you that the two forces to the right added up to 250, and I asked you what's the force to the left, it'd be a no-brainer. You'd say, hey, in order for there to be no acceleration, all the force trying to make it go to the left has to balance all the force going to the right. That means I've got to have a force of 250 over there. It's that simple. Now in rotational problems, what we have is a zero angular acceleration. This thing is not rotating to the clockwise direction, it's not rotating counterclockwise. And that means all the torque that's trying to make it go clockwise has to balance all the torque that's trying to make it go counterclockwise. Now, let's think about this rod rotating about this pivot. If that 200 newtons was the only force on this rod, that would make the rod go clockwise. And that torque is 200 times the lever arm, the distance to the pivot, or 1 meter. It's going to be 200 meter newtons. Now, if I put my spring scale there and pull up with it, if that were the only force acting on the rod, it would make it go counterclockwise. So that's going to be a counterclockwise torque. It's going to be the force exerted by the scale times the lever arm of a 1/4 meter. That tells me that the force has to be 800. Because 800 times a 1/4 is equal to 200 times 1. Check that your neighbor understood that, please. Okay, let's go back to this problem that only 7 people got right. Okay? We know that the bar is not linearly accelerating. The center of the mass of that bar stays put. That means all the force up has to balance all the force down. I got 20 newtons down, I got to have 20 newtons up. But I also know that this bar is not angularly accelerating. It's not rotating and speeding up or slowing down. And that means I can balance all the torque. All the torque that's trying to make it go clockwise, all the torque that's trying to make it go counterclockwise. Now I'm looking for the force exerted by this scale on this bar, and the force by this scale on this bar. So what I do is I draw an extended free body diagram of the bar. The first force I put on any diagram is the weight force, and I put it at the center of mass. Now I'm going to tempt you before this week is over to put it somewhere else, and most of you are going to fall for it. Don't let it be you. Turn to your neighbor and say, it's going to be you, not me. Okay? Now, I then ask, any magnets in this problem? No. So what touches the bar? Well, I've got that 1 kilogram mass pulling down with 10 newtons, and I have the 2 spring scales pulling up. Now, I'm going to balance the torques, but that's a meaningless sentence unless I have a pivot point. I have to balance the torques about a pivot point. So what is the pivot point for this rod? Is it the center of mass? Maybe. It turns out that when the rod is not rotating, I could choose my pivot point to be anywhere. It's not rotating about the center of mass. It's not rotating about this end. It's not rotating about that end. It's not rotating about a point over here. Indeed, it's not rotating about a point in Kansas. And I could choose any of those points as my pivot. However, although there are an infinite number of possible pivots, there are only 2 smart choices. Every other choice, you're going to have to solve 2 equations and 2 unknowns. There's only 2 choices that will allow you to easily get your answer. You can choose it here at this unknown force, or you can choose it here at this unknown force. Let me show you how that helps. I'm going to choose my pivot here. I could have chosen it over there. I just chose it here instead. Now, I have 2 unknowns, T left and T right. When I balance the torques, clockwise versus counterclockwise, this one here, if that were the only force acting and this bar had to go around this pivot, would this be a clockwise torque or a counterclockwise torque? It's going to make it go clockwise. This one's trying to make it go clockwise. This one's trying to make it go counterclockwise. But what about that one? If this bar were constrained to rotate about that pivot, if we drove a spike right through that end, and it had to rotate through that pivot, and I was pushing, would it go clockwise or counterclockwise? Nothing. No lever arm. 0 torque. And that's why this is a smart choice. Now, instead of 2 unknowns, I only have 1 unknown, because this one doesn't give me a torque. Okay? So if I balance all my clockwise torque with all my counterclockwise torque, this gives me 0. This force is multiplied by its lever arm, the 5 meters to the pivot. This force is multiplied by its lever arm, the 0.8 meters to the pivot, and that's all the clockwise torque. This counterclockwise torque is this force I'm looking for times the lever arm, which is the distance to the pivot of 1 meter. If I solve that equation, I get 13 newtons. Well, the total upward force has to add to 20, so that one has to be 7. Check to see if your neighbor is one of the 7 people in the room that got that answer at the beginning of class. Do a buddy check. Okay. What I've got there is 7 newtons and 13 newtons. Okay? 7 and 13. Now, I could have chosen this point as my pivot, in which case this would give me 0 torque. This would give me a clockwise or counterclockwise torque about this pivot. Counterclockwise, this would be counterclockwise, and that would be clockwise. Okay? So either way you want to do it. Okay, why don't we stop here? We'll pick this up on Wednesday.